Unit 6, Chemical Reactions, Chapter 3, has us looking at some different chemical reactions that we have yet to cover. Some of them are very important for our everyday life, and some are just used as indicators. We'll look at some, and some things will be required to do some other parts of it too. First one, fairly important, especially in the upper Midwest. Especially, we use what's called burning of organic compounds. Since we use a lot of these to heat our homes, such as propane or methane, and even cellulose will work as well. And that comes from the form of, what you're doing is you're having those organic compounds, as we looked at in Unit 4, that compose of only carbon and hydrogen. So these are the majority of what we're going to have and see. Now, it does not always have to have oxygen. Sometimes they will. When we burn in air, it has to react with oxygen. If oxygen isn't there, the reaction doesn't work. As if you ever put a glass jar over a candle, you'll notice that the flame eventually goes out. That's because all of the oxygen is not there. And so therefore you have to have that. Your car burns its fuel, and therefore it needs to have an air intake. Otherwise, otherwise you wouldn't have the combustion process to happen. And you need to have that correct oxygen to fuel ratio that we'll be talking about in Unit 7. So our burning of organic compounds always gives off, especially if the reaction is fully done, carbon dioxide and water. Okay, for our class, we are only going to focus on complete burning of organic compounds and not half burns or some other thing, and that would then therefore give off incomplete burning of organic compounds, and that gives off some other carbon and oxygen and hydrogen compounds that might make things a little bit confusing. So we're going to focus just on the burning of organic compounds, and therefore they will always give us carbon dioxide and water. These are always going to be the products of a burning of organic compound reaction. The one thing that needs to happen is that oxygen needs to be there, at least as one of the reactants. Now, what the organic compound is made of, it has to have carbon, and it will also have to have hydrogen. Sometimes the oxygen will be there, sometimes it won't. And also, the state can vary, meaning it can change. It can be a solid, it can be a liquid, or it can be a gas. So let's try it out. We're going to have some ethanol here, and if I'm going to burn ethanol, I'm going to need oxygen gas, there, and the two compounds that I have as products are going to be carbon dioxide and water. Now, as we see, this reaction is not balanced. One of the tricks that I'll give you is that you should balance oxygen in these reactions last. Make sure that oxygen is done last. And so, what we do is we will balance our chemical reaction, as we have been. And so I know I can see I have 2 carbon, and I will need 2. And I also see that I have a total of 6 hydrogen on the reactant side, and therefore I will need a 3 there. Now, if I looked carefully, and now we'll have 4 oxygen plus 3 oxygen, well, that gives me 7. Minus 1 for that oxygen right there gives me 6, and therefore I just need a 3 total to make a total of 7. The next one that we have is one that, again, many of us use to heat our homes, and we see that we will need to have oxygen present. And the products will be carbon dioxide and water. As always, those are always going to be the products. And if I see again, I can, oh look, it's not balanced. Therefore, I'm going to need to put a 2 in front of hydrogen. And now that means I have a total of 4 oxygen. And therefore, all I need to do is put a 2 in front of my oxygen on my reactant side. The next one, I have much more complex carbon containing organic compound, and I will put my oxygen, because if I'm going to burn it or completely oxidize it, it needs to be there. My products are always, again, going to be carbon dioxide and water. Now from there, I still need to balance it. Now the numbers are going to be just bigger than ones that we've used before, but the method is still the same. And so I still just put an 11 in front of my carbon dioxide, put an 11 in front of my water on my product side, and now I count up my oxygen to see that I have 22 plus 11 is a total of 33. Well, I have 11 of them over there already, so I just need 22 oxygen. And therefore, if I put an 11 in front of my oxygen on my reactant side, it balances out. What type of reaction is described by the following equation? Before we can really discuss double replacement reactions, we have to determine whether an ionic compound is soluble or in water or not. Soluble means it dissolves, or a better term is dissociates. There are 5 rules of solubility. If you look them up online, you're going to find that they can be anywhere between 5, and I've seen them as high as 14. I suggest learning these rules. I even suggest learning these rules and having them in order as well. And since you get to use your notes on most of your assessments, I would highly suggest having these written down. First rule is that all group 1 elements are soluble. So all group 1, rule 1, group 1 is usually how I say, that is not the correct way for writing out ammonia. It's NH4 with a positive charge. That 4 needed to be subscript. So all lithium, sodium, potassium, and ammonium salts, anything that has that, does not matter what the anion is, the negative ion, on that. If you see a group 1 or ammonium at the beginning, that means it is going to be soluble. These are the only ones that actually deal with the positive or cation versions of that. Number 2 says that all acetates and nitrate salts are also soluble. So, for chance, say you see a compound that has a acetate in it. Now, if it has a sodium acetate, that means it is soluble because of Rule 1, not because of the Rule 2. Rule 2 just so happens to be there. So the rules actually go in order. Now, if you saw one that, say, was a calcium acetate or a calcium nitrate, that would be soluble because of rule number 2, because of the acetate or the nitrate, not because it's a calcium, because as we'll see, calcium sometimes will be insoluble. That means it is not going to make a solution. All halides, that's group 17, are soluble, except for silver, mercury, and lead. When we talk about halides, a lot of times we will use the X, as we see here. the X to determine that any of those will be there, seeing any of the halides, since they react so similar to each other. So all halides salts are soluble unless you have a silver halide, a mercury 1 halide, and a lead halide. A lot of times, suggestion is, if it's something at the beginning, a metal that you probably shouldn't ingest, chances are it's insoluble and you shouldn't have that. And so we'll see those are kind of what you look at. And it is usually the exceptions that will get most students. Rule 4, SO4. That's how, at least how I memorize it. Rule 4, SO4. Salts are soluble, with the exception of strontium, barium, and lead. You could probably put mercury in on that too. However, we don't deal much with mercury in the lab, so we don't tend to have it written down in our solubility rules. Try to keep it to ones that you're going to see in the lab. All other salts are insoluble, meaning they're going to make solids. And therefore, you're going to look at the carbonate, the phosphate, the sulfide, the oxide, the hydroxide, with the exceptions of the same calcium, strontium, and barium, sulfides and hydroxides. They are soluble. Now, it's not maybe easy to get them into solution, but they can go into solution. Again, I would highly suggest looking at these, writing them down, memorizing them, and so that you have them in your notes. It will make some of the assessments that you have later on much easier. Predict whether the following are soluble or not. Within this, we're also going to not just say if they are soluble, we're going to say the why are they soluble. So the first one, sodium carbonate. Now, if you look at what it's made of, you can start to potentially contradict yourself. So once you have a rule that says that it is soluble, you stop, do not pass go, do not collect $200, just kind of like the Monopoly game. We have, this one is soluble, meaning it's going to be AQ for aqueous. Why? It is that way because Rule 1, Group 1, we have a Group 1 element. B, where you have tin 2 acetate. Again, not always sometimes easy, but it is soluble. And therefore that means that it's aqueous. And the reason why is rule number 2, acetates and nitrates. Even though we're not dealing with the nitrate here, we still say acetates and nitrates. C, we have silver 1 chloride. If I look at my rules and see, is it a rule 1? Nope, because silver 1, even though it says 1 in the name, it is not part of group 1. Chloride is not an acetate or a nitrate. So rule number 3 says that all halides are soluble, except for silver, mercury, and lead. So this is insoluble, meaning it's going to make a solid. And why? Rule 3 exception. D. Rule 1 says that group 1 and ammonium, barium is not one of those. Rule 2 says acetates and nitrates, well, they both end in ATE. Well, this is sulfate, and that is SO4, Rule 4. And therefore, I actually have, again, an exception to the rule, and therefore it is insoluble, meaning it is going to be seen as a solid. And why? Rule 4, exception. And the last one says iron 3 carbonate. Well, iron 3 is not a group 1. Carbonate, even though it has an ATE, is not an acetate or a nitrate. It is not sulfate, and therefore, if it goes through all 4 of the rules, then that means it is insoluble. Therefore, going to be a solid. And why? Rule 5. Which of the following products of a double replacement reactions would not form a precipitate, meaning they are soluble? Now that we have the solubility rules figured out for the most part, we can use them to predict whether or not a double replacement reaction is going to occur. Double replacement reactions occur when 2 soluble salts or 2 liquids are mixed in a precipitate forms. This is one of the rules that we talked about at the very beginning of the year, where we had the rules or determining whether or not a chemical reaction occurs. And therefore we have 2 solutions making a solid. In this case, a solid is the precipitate. Some examples of this is that we can see here that we have barium nitrate mixing with sodium sulfate. Now, a lot of times when we look at these types of reactions, we wonder, how does this actually happen? Well, what we see here is that the barium splits into its ion, and the nitrate also splits into its ion, and the sodium and the sulfate do the same. This should be a plus, not an X. And notice that the 2's and things like that go away. And so what we have is that they, just like square dancing, they swing their partners do-si-do. That means barium is going to dance with sulfate, and sodium is going to dance with nitrate on the other side. And so what we don't have written down is the sodium nitrate. And now when I look at this, I can see that barium sulfate, well, we have to determine what it is. Is it going to be a solid? And if we look at rule number 4, because it's SO4, we're going to see that it is a solid. That is going to be our precipitate. The sodium nitrate, that is going to be aqueous. It's going to look like just water in the reaction. So we can see that they swing their partners do-si-do, doing their flip-flop. The iron 3 chloride is mixing with silver acetate to make iron acetate. And, well, again, how does that happen? Oh, almost forgot. We have to balance our previous reaction. That would be just terrible. And so we now have our iron 3 chloride, the minus, the silver acetate, C2H3O2. They swing their partners do-si-do. That's why iron is with acetate on the other side. And that means the silver chloride comes to bond. Now, if we are wondering what it is, let's look at our iron acetate. Well, Iron is not a group 1 element, so we have to go to rule number 2. Acetates and nitrates are soluble, so therefore it is aqueous. It's just going to look like water. Silver chloride, however, is the solid. It is insoluble, therefore it is going to look like the solid, and it will be a precipitate. This is, again, not balanced, and therefore we do need to balance this chemical reaction as well. Erase some of the stuff above so it makes a little bit easier sense. And so I can see that I need to have 3 in front of my acetate and a 3 in front of a chlorine. And so this isn't always going to be super straightforward. And so what I can see here is that if I put a 3 in front of my silver acetate, and I will need to put a 3 in front of my silver chloride. And now I have it all done. Now, if a precipitate can't form, that means no reaction is going to happen. A lot of times students will say nothing happened or there's nothing observed. And so if we look at the reaction of sodium nitrate and calcium acetate, that would give us just the potential products, and sometimes this is what a lot of students need to do, is actually look at it and see what the products might be before they even determine that there is no reaction. And so they need to go through and determine that calcium nitrate is soluble and sodium acetate is also soluble. Therefore, no reaction. And you can use NR or writing out no reaction. Determine whether the following occur, and, if so, write a balanced chemical reaction. Sodium nitrate reacts with silver acetate. Now there are some rules that we do know that never have exceptions. Ones that have nitrate and acetate are going to give us no reaction. But for practice, we'll write it out. Anyway, so I'm going to have my sodium and my nitrate, silver, and acetate. I'm going to, that is not a positive there, that should be a negative. Right there. And so I can see the charges cancel out, so it's just NaNO3 plus silver acetate O2. My potential products, meaning when I swing my partners do-si-do, I will have a sodium acetate and a silver nitrate. Both of these are soluble. Sodium acetate is soluble because of rule 1. Silver nitrate is soluble because of rule 2. Therefore, no reaction. Now, to do the next one, I'm going to have to do a little erasing here, because I need to see, again, calcium chloride. So again, it'll be easier to write some of these out, such as this. So it will remind you of doing some of your naming. That's why the naming was so important. Ammonium, NH4 plus, and the hydroxide. And so now I can see, oh look, my charges don't match up. Therefore, need to have CaCl2 plus NH4OH. If we swing our partners do-si-do, we'll have a calcium hydroxide. The 2 goes on the outside. And a ammonium chloride. Now I need to determine whether or not these reaction is going to happen. Now calcium hydroxide, we look at it and we think, okay, well, it's not a rule 1. It's not, hydroxide is not rule 4, not rule 3, not rule 2. So, therefore we look at it and say that it would be insoluble. But one of the exceptions to rule number 5 is the fact that calcium, barium, and strontium hydroxides are soluble, and therefore this is a no reaction. If I could spell that correctly. Ha. No reaction. Because calcium hydroxide and ammonium chloride are both soluble. This is soluble because of rule number 5, exception, and rule number 1. Here's some more. Lead 4 acetate reacts with potassium sulfide. Just like before, writing these out to determine their charges and how to put them together when it comes to writing out the chemical reaction, if necessary. And potassium NKS2. Oop, only need 1 minus. Alright. Well, there I can see that the charges do not match up, so therefore I write lead 4 acetate plus potassium sulfide. Again, charges don't match up. So K2S. Those are going to give me the potential products based on what I have here. Swing my partners do-si-do. We'll say lead sulfide. If I look at that, though, it's going to be a 2 and a 4. Therefore, it's going to reduce down to, say, just like that. And and potassium acetate, 3O2, which I know to be aqueous. Now lead 4 sulfide, now that one is insoluble, therefore going to be a solid. And if it's a solid, that means this reaction does happen, which means I now need to balance out my chemical reaction. Now to balance this out, I'm going to need to put a 4 in front of my potassium acetate. And then I'm going to need to put a 2 in front of my potassium sulfide. And it now balances out right as rain. The next reaction has me dealing with barium chloride with ammonium NH4 plus and our sulfide. Now barium chloride, we'd see that my charges match up or don't match up. Plus ammonium sulfide, put put that in parentheses. That's why the naming was so important in Unit 6. And so we can now see that the potential products would be a barium sulfide and a ammonium chloride. I didn't put any numbers on the barium sulfide because, again, the charges match up, the +2 and the -2. Now when I see these, a lot of times I'll look at it and go, oh, my barium sulfide should be insoluble, but it is an exception to one of the rules. Therefore, it's no reaction and again, ammonium chloride would also be soluble because of rule number 1. So you do have to again be very careful of which one does what. Which reaction will not produce a precipitate from aqueous solutions. Neutralization reactions are ones that we have acids and a base. Therefore, we have a acid, compounds that contain the hydronium ion, the H+, and a base is ones that usually will contain the hydroxide. Now there are others that will give off, and that is written completely wrong, H2O. Now what's interesting about these is that you're always going to get what will look like two solutions, just making two solutions, but this is where knowing what you're putting in is so important. Because if we look, water is a liquid. It is a neutralization. A new thing is being formed that is not just going to be an ion. So it is very important to really be able to recognize your acids and your bases. When balancing neutralization reactions, it's highly suggested that you balance out the salt first, that is the NaCl or whatever other salt that you might have on the product side, and then balance out the water last. Is that it will a lot of times tell you how many hydrogen and how many oxygen you need to have, and therefore the coefficient that will go in front of that will be easily determined. So let's try some out. We have hydrochloric acid mixing with sodium hydroxide. Now a lot of times I've seen students write these out just like they did with the double replacement reactions, and for what they end up writing is HOH. Well, a lot of us will recognize that as H2O. And the other part of my product would be NaCl. And if I look and count everything up, it'll show that it's balanced perfectly, just like it should be. The next one has us taking sulfuric acid and mixing it with a calcium hydroxide. Well, if I do that same thing of the swing my partner do-si-do, I'm going to get water, which will be my liquid. Should put that up there. And the other part is going to be a calcium sulfate. Now, you might notice that I'm not writing any of the crisscrossing because calcium has a +2 and sulfate has a -2. Now, when I look at this, though, it is not balanced, and therefore I need to balance it. So I look to see if my calcium and my sulfates are balanced, and they are. So therefore, I need to see how many hydrogen and oxygen I have. I see that I have 4 hydrogen and 2 oxygen. Therefore, I need a 2 in front of my water. The next one, I have phosphoric acid and a potassium hydroxide. Water is going to be one of my products. And then I'm going to have a potassium phosphate. Now this one, I need to pay attention to my charges. That's where the 3 comes from the potassium phosphate. That's going to be an aqueous solution, just like that would be. And that is an aqueous as well. But I definitely do not have a balanced chemical reaction. So the first thing I'm going to do is balance out my salts, which means I need to put a 2 in front of my, 3. Almost really messed this whole thing up. Put a 3 in front of my potassium. Now, when we go through this, I can see that I have 6 hydrogen and 3 oxygen. Therefore, I just need a 3 in front of my water, and it's done. Predict the missing product in the following unbalanced chemical reaction. Well, that concludes Unit 6 and the chemical reactions, not only just Unit 6, but Unit 6, Chapter 3. The next unit we'll be covering in Unit 7 will be using these chemical reactions, using the balancing of these chemical reactions to do and bring it back some of an idea that we talked about at the end of Unit 5. So next unit, Unit 7, takes ideas from both Unit 5 and Unit 6 and brings them together for one of the most important parts of chemistry, and that is stoichiometry.